Now we have answered the first question about the structural small world. And answering this question, as we just saw, it leads to a deeper question, and indeed the more surprising observation out of the Milgram experiment in the late 60s, and that is the algorithmic small world. One model by Kleinberg, 2 years after the Dodds Strogatz model, can be described briefly as follows. And then we have a homework problem to go into further detail about that. So now we would like to find out the quantity little l, which is the length of the greedy search path in a social network. Okay, and we'll want this number to be small and also grow slowly as a function of number of links, just like a big L. In Kleinberg's model, it says that true, we will have longer path, but the longer the path is, the less likely it will be established. Okay, that's the starting point of Kleinberg model to explain these small little l's. Well, how less likely? Let's say if the distance is denoted by r, which could be the physical distance or some composite metric of social and physical distance, then the probability that such a long-range link exists is r to the minus alpha. So alpha is some parameter that controls the rate of decay of the likelihood of the longer path. And then it turns out that Kleinberg showed if this rate of decay, alpha, is exactly equal to the dimension of the space, for example, in our world 3 dimension, in the world of, say, a grid, 2 dimension, in the world of a line or a circle, 1 dimension, then if alpha is 3 or 2 or 1 in these 3 different cases, or in general, as long as alpha is exactly equal to the dimension of the space in which the network resides, then algorithmic small world will hold. This little l will be small and grows slowly as a function of n. So why is that? Again, the proof is in the homework, and we'll go through a similar model in just a minute. But intuitively, what's going on is the following. That if you look at, say, two-dimensional space, or in general, k-dimensional space, okay, then you look at a ball of radius r, then you look at another ball of radius 2r, and then you look at how many more people that will live in this space. Okay, the probability of having a linked one of these nodes will drop as r to the minus k, and yet the number of nodes living in the space, assuming some evenly distributed node location, will be proportional to r to the positive k. So as you go farther out, there are more people that you might know, even though the chance that you know any one of them is smaller. And it turns out if these two growth and decay rates cancel each other out, then you pretty much have a constant chance of number of people that you will know as the space grows. And that turns out to be the key idea. The number of people going up compensates for the smaller chance of knowing any individual as the social circle expands. And that's what's underlying this result. Now you may say this result is a little too brittle, because we need alpha to be exactly equal to the space number of dimensions, k. It can be a little bigger than that, to say k plus 0.001. It cannot be k minus 0.1. And a part of this brittle nature of the result is due to the fact how we define algorithmic small world. We want L to grow as a log, or at most a polynomial of a log function. Okay, and part of the reason is because the way we construct the likelihood of the longer path. In the advanced material part of the lecture video, we'll talk about yet another alternative model to explain algorithmic small world without this brittle nature. But before then, we will first talk about a variant of Kleinberg model called Dodds Newman model. This is an extension of the Kleinberg model, and this is a model that tries to explain algorithmic small world, whereas the Dodds Strogatz model tries to explain structural small worlds. In Dodds Newman model, you have the following character of a human society, of the social network. Okay. You got people living in groups of G people per group. So each leaf node here is a group of people on this rectangle, and each individual is represented by a node, some of them labeled here. Okay. And then you have a total of n people in the whole world. So you got n over G leaf nodes, these villages or communities. Okay. Let's assume for simplicity's sake that this is an integer. And then we can therefore say, take the base 2 log, because this is going to be a binary branching of a tree structure. So base 2 of the log of n over G, that will be the number of levels. And each level will be indexed by little m. So in this case, suppose we have, say, 80 people in the world, and each society can host 10 people, then we'll have altogether 3 levels. Okay, m equals 1, 2, or 3. Okay, this is 1 level, 2 level, 3 level. And this level denotes the chance that you know somebody. For everyone within the same community, there is a direct link. You can directly talk to each other. And if you want to reach, say, send the mail to somebody else outside of your own circle, then you have to find the first common ancestry. Okay, we use ancestry to denote the tree structure here. These are the children nodes of this parent node. So you want to say, if A want to talk to B, I can directly talk to him. If A want to talk to C, C is not in the same community. So I have to find out what is the lowest common ancestor node. Well, it's 1 level above, is n equals to 1. Okay. What if I want to talk to D? Then I actually need to find the lowest, the first common ancestor, that's level m equal to 2. And if A want to talk to E, turns out I need to go all the way to level m equal to 3. Okay. And the idea is that the probability that 2 people know each other decays exponentially in m, the level of the first common ancestry node. So probability P that 2 people separated by m level of first common ancestry, P sub m, okay, is proportional to exponential decay 2 to the minus alpha m. Okay, so bigger the m, smaller chance that you know each other, and the rate of decay is alpha. As you can smell, this is very similar to the Kleinberg model. And indeed, you can view this kind of tree as a one-dimensional world, and we will see that we want alpha to be 1. All right, so this is proportional, and therefore, to be precise, we have to write down the normalization constant, and therefore is P sub m equals to some normalization constant k times 2 to the minus alpha m. K is such that the summation of all the p's across all the m's equals to 1. Okay. All right. So now we can do the following. First, let's find out expected number of people reachable, okay, within the mth ancestor. Denote that by big N sub little m. Well, that's really a product of 3 things. First, the probability of knowing someone across m ancestor level. Second is the number of communities that you can reach, which is 2 to the power m, by traversing m levels of ancestors. And the third factor in the product is G, is the number of people within each community, which is assumed to be the same across all communities. So it's a factor, 3 factors multiplied together. The chance you know someone there, and the number of communities times number of people per community. Okay. And we are going to write this as 2 to the power 1 times m to highlight we're really raising 2 to the power 1 times m. And we'll later come back to this 1 because it will be playing a critical role to show that alpha needs to be exactly 1 for algorithmic small world. Now we can substitute the expression for p sub m and have the following expression then. G times k times 2 to the power 1 minus alpha m. Okay, there's an m here, and then for p sub m there's a minus alpha there. So this is a constant, this is normalization constant, therefore this decays with 1 minus alpha as the exponential decay rate. Now, what we want to do is to say we want to compute the average, the expected length of the social search. So that's the little l. Well, let's see. If I want to reach someone, I want to find out basically someone within my same community that can hop over, knows somebody out there, right? If I know that, then I'll go straight. Otherwise, I have to find someone else to go to that community. Okay, and the expected number of people you need to pass on internally before you can reach to someone in the mth community is 1 over nm. And then passing through all the m communities is summing over little m. And since we know the expression of nm, we can write out this expression, which is 1 over kg, the constant pulling out of the summation, summing over from n equal to 0 to log of n over g minus 1. Okay, from the 0th level to the highest level times 2 to the power alpha minus 1 m, which turns out to be 1 over kg times the following expression, n over g to the power alpha minus 1 minus 1, 2 to the power alpha minus 1 minus 1. And say this is the answer, all right, except we know n, g, and alpha, but we don't know what k is. K is just normalization constant. We need to express it as a function of parameters that have physical meaning. Well, one way to express that is to say, if we look at the average degree of a node in this graph in the tree is simply summation of nm's over m, which turns out to be k times g n over g to the power of 1 minus alpha minus 1 to the 1 minus alpha minus 1. So now we can express k as a function of average degree and the constant d, g, n, and alpha. You can substitute this over here, and then you get the following expression. L equals 1 over d bar, which is some constant, times n over g to the power alpha minus 1 minus 1 to the alpha minus 1 minus 1 times n over g to the power of 1 minus alpha minus 1, 2 to the power of 1 minus alpha minus 1. So now it depends on whether alpha is bigger than 1 or smaller than 1 or equal to 1. In fact, if alpha equals to 1, this derivation doesn't hold. Okay, we have to take a look at this expression again, and we'll come back to that later. The moment we write this in this expression, we have assumed alpha is not exactly equal to 1. But it could be bigger than 1 or smaller than 1 strictly. As you can see from these two mirror image expressions, either way, you see L grows like what? Like n over g times the power alpha minus 1 absolute value. If alpha is bigger than 1, this term will dominate, this will go away. If alpha is smaller than 1, this term will dominate and this will go away. Either way, we can say L, the interest quantity, grows as n over g to the power alpha minus 1, which is not a logarithmic growth in n. L as a function of n is not algorithmic and therefore not a small world. At least not algorithmic small world according to the greedy search method. So our hope is that what if alpha exactly equals 1. Well, if alpha exactly equals 1, what would happen? Let's go back to this expression. Then nm in that case becomes nothing but gk. And this is the key part. It is independent of m. And that's exactly the intuition behind Kleinberg result we just mentioned. For the appropriate decay rate of forming relationships over longer distance, you say that as the distance becomes longer, in this case m becomes bigger, I have a smaller chance of knowing people, but then there are more people for me to know. And if the two terms cancel each other, and therefore the number of people I may reach is independent of the distance, in this case is just g times normalization constant k, then something interesting happens. What would that be? Well, let's look at what L is. Okay, in that case, we can find the following. L is just 1 over summation of 1 over nm, which is simply 1 over gk times the summation of ones. How many times? Well, log n over g times. Okay, and now we can use the same trick to express k as a function of the average degree, and then we see the following. 1 over d bar, the average degree, times log of n over g squared. This expression, as you can see, function of L as a function of n is logarithmic. Well, not exactly, it's square of logarithmic, but a polynomial of logarithmic is still good enough. In particular, this is an upper bound. So we have a small world, a algorithmic small world, because the social search L by greedy routing distance is a function like log of n, or square, upper bounded by the square of log of n. And what really happened is the following behind the mathematics, is that if the rate of decay of the probability of knowing someone at over distance m goes down at just the right rate, then it cancels out by the effect of having more people over longer distance out there. And if the two exactly cancels each other, then you get a constant term for n sub m, and that leads to L becoming a logarithmic function as opposed to a polynomial function. So here's a simple example. As I plot L as a function of n over this large range, you see that when alpha is very close to 1, you see a very slow growth. Okay, when alpha deviates from 1 a lot, then the growth is much, much faster. A better way to look at that is think of L, okay, as a function of fixed n, now vary over alpha. You see, when alpha is exactly 1, that's where it hits the asymptotic growth rate of log n, or squared of that. For a numerical example with the fixed n, we cannot see the effect of that, but we can see that is small in absolute terms. L is very small, less than 5. And then as alpha deviates from 1, then you can see L becomes much bigger. So either we look at it as a function of n, look at the growth rate asymptotically, or fixed n, look at a function of alpha and look at the absolute value. Either way, you validate what we just demonstrated through this numerical example. So now we come to the summary part. We looked at the structural small world first. We want small short path to exist and yet large clustering coefficient to be maintained. Turns out that a regular ring with a little randomization to induce long-range links suffices. When P is small, then we get a large clustering coefficient C and a small big L for the shortest distance. And the reason of that is because this is an average quantity, it's not destroyed a whole lot by small randomization, and yet this is an extremal quantity a little randomization can help create short path. And the reason that assumption is okay in this different way of defining metrics is because of the bigger surprise out of the 6-degree separation experiment, the algorithmic small world, that short path not only exists, but also can be found with local information through, say, greedy routing methods. And we look at the social search, little else, behavior in Kleinberg, and also the Watts-Newman models. These models might be brittle. Advanced material will look at a less brittle model. All these models are so-called generative models because they can provide a mechanism to generate a network with the desired behavior, in this case, small world. They are explanatory models because they explain what we observe. And they are useful, but they are also dangerous. As we will see in the next lecture, when we try to reverse engineer to explain or generate another famous phenomena in network topology, not small world, but scale-free network, or the long tail distribution of no degrees, then we'll see that if we do not add enough domain-specific functionality model, then these generative models can lead to a misleading conclusion.